Start. Hi everyone. Um, I'm glad that was muted because my chair collapsed and I got really mad. Nice to see you. Good to still see some people here after you know the time given. I just around this time of term, everyone kind of gets tired and they all start to disappear. It's definitely time for a new chair. Old Betsy. I've moved this chair. I've moved since I bought this chair. I think I've moved house 14 different times. Um, Moved like where I lived. So it's an old chair. The very first move it did, I think, was I wheeled it from Maroubra to Kensington along the footpath uh, to move houses. So I'm very sad. I'll be very sad to see it go. Now, just before we jump into today, two things I just want to preface today with quickly first. One is just about some of the comments people made last night. So I had to look through the feedback last night, and there was quite a lot of people who said that they didn't feel like we went through the content last night in enough detail. And I totally get where you're coming from. I think I just wanted to give some context to that. So, with everything in this course, we can always go through things in a substantially more detail than we do sometimes. We could probably talk about custom iterators for 2 or 3 weeks if we wanted to. Generally speaking, our attitude is to try and go as deep into things as we feel that you need for accessible content, which is basically the assignments or the exam. Um, where week 8 and 9 differ from the rest of the weeks is that we don't ask you to do it. Sorry, we don't ask you to do a ton with this stuff. So unlike custom iterators and templates where we like really dig into everything, the advanced template stuff we did last night is very much like it really doesn't, it's not going to have a massive impact on the rest of your time in this course, right? The way it manifests in your assessments is substantially less than the other stuff. So therefore, we'd rather cover a broader array of topics in a little less depth. So that's on last night's stuff. I know some people will still not like that, but I hope that gives context. That's not us just deciding not to go through it. It's just a choice about how much we go through certain content. Yeah, exactly. And the second point is that today's topic, which is called advanced types, which I'll pull up now. This particular lecture is probably the most mishmashy of lectures in the course. It's probably the first one I would look at changing. We're going to cover a bunch of things. By a bunch, I mean a few. First one is decal type, which is a way of converting values to types in a sense. We're going to cover type transformations, which is a lot like type traits last night. All the same kind of principle, just different usage. We're going to cover binding, which is an extremely confusing but relevant topic, which we touched on in the Tute 7 for anyone who's watched the Tute 7 recording. I actually talked about this a bit then. And then we're going to talk about forwarding, which is a really interesting application of binding. These aren't my strong suit topics though, so I think I just want to preface that in advance. There'll be a few times today that the answer will be I don't know, because these are getting really theoretical. Not theoretical. These are just getting like a bit more obscure and kind of academic. And I used that word a couple times yesterday, and I think just to contextualize, when I said to people that these topics are academic, what that means is not like they're for the smart students. What it means is that, like, if you think about like research versus like practice, it's like the practice stuff is what you go and do every day with, and some of the academic stuff is more, most people don't come across this or have to think about this much in their day-to-day whatever, So like a lot of things in this course, as we get deeper into the course, like around this time, you'll find that if you were to go do some work with C++ in a research context or industry or this or that, like, not that it doesn't matter, but for the majority of standard use cases, you won't have to think a ton about things like type traits and type transformations. And if you do, often it's just to make your code cleaner and better and all of that. So the point I was trying to get at yesterday was just that the way I kind of view a lot of the week 8 topics, maybe with the exception of binding, because I think binding is pretty important. A lot of it, like if you just never watch these lectures, you'd probably be okay, right? Like you would never be like, oh damn it, I really don't understand something. Whereas like if you miss stuff on templates or you miss stuff on smart pointers, like all these things, you definitely feel a very real, obvious hole in your knowledge. So when I say it's academic, I just mean, you know, you'll be fine. And a lot of the fun of doing this is to think about the language in a bit more of a theoretical, broad way, rather than just being like, if I'm not using it every day, I don't care about it. Like that's a non-academic view of this. Anywho, that was a bit of a babble. Today, so one of the first things we're going to talk about is decal type. Now, this concept is easy to understand at a high level, a bit harder to understand at a lower level, mainly because we've started stripping parts of this topic out over time, and in some ways that's made it easier, but some ways it's made it harder. For instance, previous offerings of the course, we used to go into more detail about L values and R values and some of the subtypes they have, but in essence, decal type is a built-in function into C++ that essentially allows, maybe we could start with an example. It essentially allows you to take a variable or a named item, whether it's, an R value or an L value or whatever, and to get the type of that. So instead of writing something here like int or auto or double, you can actually say, no, the type that I would want to put here is actually the declared type, which is what decal type stands for, of this particular value. So in a program like this, for instance, if you want to say int x, but instead of it being an int, you actually want to say, I just want x to be the same data type as whatever I is, you can just say decal type I of x. So it's really a way to replace typings by using name values. You can do it broader than that, but that's the use case of it. Over the next few slides, we'll talk more about where you can use it and kind of how this topic can be broadened. But at the highest level, it's similar to a type of function for C++. Now, if you've used a language like C is type of in C? Oh, maybe anyway, like Python has a type. I can't remember which language has a type of. I'm not sure if it's JavaScript, and I'm getting confused. But it's like in other languages like Python, you have this ability to do something. Like I was writing some Python this morning for someone, and you can say like, if type of A equals int, then do something. Now, where I want to point out the difference between where you may have seen something like this is what this is saying is this is like, I want to take a named item, like a piece of data, and I want to find the type of it as a value. So you can actually do value operations with this, like equals. Where decal type differs is that decal type is like a type. So if you imagine in a language you have types and values, right? And when you say int a equals 5, you're essentially saying, this is one way of thinking about it, you're essentially saying type value equals value, right? A is a value, R is a value, L value, R value, whatever. Int is not an L value or an R value, it's just a type. Just like int, double, whatever, T, generic types. So when we're dealing with types and values, in a lot of other languages, when you have it like a type or a type of, depending on the language, like if you're using something that's loosely typed like Python, type will actually return you a value that you can interact with. You can put it inside of if statements. Whereas in C++, it's more like, C and type of, where it's actually getting you a type. So in C++, if you did something like, say, you said int I equals 5, it makes no sense to say if decal type of I equals int. That's not valid code, right? Like that's just not how the language works. You don't do binary comparisons, and equality don't take in types, they take in values. So this here is a type, not a value, which is which I guess is kind of one obvious and key difference. The real question though is when you pass something in, like if you pass a variable in, like an integer variable in, decal type will give you an int. The real question is what type does it give you? So if you look at these slides here, you actually see there's 4 different outcomes here, which is that you have type T, T reference, TR value reference. Well, I'll call this TL value reference, TR value reference, or type T here as well. Now, I think in the past I've tried to go through these rules in a bit of detail, but it can get very confusing very quickly. But the point is that if you have something like, if you have something like an int I equals 1, and then you say int j, or int reference to j equals I, or then you say int, k equals standard move I, and all these kinds of things, well, that's still going to give you an int, but it's like, these are all kind of different instances of int. So it's like, if you take I, j, or k, and you decal type it, you'll get an int, right? They're all ints. They're all different types of ints, so you'll get an int. That part's the easy part, right? That part's quite straightforward. The harder part about decal type is, are you going to get just a standard T value? Are you going to get a T reference, which we call an L value reference? Or are you going to get a TR value reference, right? And that depends on the type of thing that you enter. So Void's already asked, does decal type happen at compile time? And the answer is yes, right? So with languages like C++, types are essentially all about compilation. So anytime something has to do with types, you're pretty much always dealing with compilation. That's not always true, but it is a very broad general rule. Pretty much all kinds of types and checkings and stuff happen at compile time. So here's the thing. These are kind of a summary of the rules. It's like if an expression E is any of a variable, like a standard variable, a static member, a function parameter, then the resulting type is T. So if you just say int I equals 1, then it's of type T. And then you get into some weirder rules where, like, if the type you're decal typing is, say, a reference, like what we had in gedit here, which was J, then that's going to be, the actual decal type will be a T reference, right? So that reference will carry over. Then it gets more complicated once we get into like X values and R values. And again, I'm intentionally not going to start explaining this because it's not accessible, right? It's not accessible. And we could talk about it for a while. Two things I've done though, if you want to read more on it, which some of you will, is that firstly, to understand the decal type rules, we have to understand that in C++, the types of values we have are more complicated than L values and R values. It gets a little bit more thorough than that. I have linked a really something I look back on if I ever want to refresh my memory, which is essentially how they describe R values, L values, X values, GL values, and PR values. And there's a certain amount of inheritance relating to these in terms of like, they're not all 5 totally disjoint types. Some of them are kind of subset-ish of each other, or they have some kind of complementary value. But this is like, these are kind of some descriptions. This is kind of one of the more simple ways I like to understand it. Some of them are quite funny, like, a PR value is an R value that's not an X value. And then you think, well, what's an R value? An R value is an X value, a temporary object, or a value that is not associated with an object. Now, we've kind of explained R values before without the X value stuff, right? We've said R values are essentially something without an address, was how we simplified it. It's a temporary object that has no address, like a literal, or a value not associated with an object, like a literal a lot of the time, or something that's standard moved, something that's kind of floating through the air and isn't really tied to a specific thing. So then to understand what a PR value is, they say, well, it's an R value that's not an X value. And you think, okay, sure, what's an X value? And then it gets kind of complicated, how to separate all these out. So Nathaniel in the chat said, a better description to split. A PR value is just information on how to construct an object and isn't an object yet. An X value is an R value that is actually an object and has an address, etc. I'm sure there's more coming, or maybe not. But the point is, the distinctions here are more valid than kind of the simpler ways we talk about it in the course. Though in the course we just kind of deal with, you have L values and R values, and L values have addresses, R values don't. Which is actually a really easy way to understand things, because a lot of compiler errors will give you information in terms of like, trying to assign R value this. So it's a great starting point, but if you want to learn more, that's where you can look, or you can do some more Googling. But then also the actual decal type rules, what I have on this slide here is just a summary of the C++ decal type specifier anyway. So decal type can take in some stuff, and here is a full explanation of how it's all kind of derived in terms of like what we have on the slides is what's here. If it's an X value, then it's that. If it's an L value, then it's that. If it's a blah blah, then it's that. Though generally speaking, the main things to take away are that, and this will cover you for the majority of cases. Usually you're going to mainly be interested in 1 and 2, which is kind of like, if you have an int of some sort, decal type of that value will give you an int. Decal type of that name, I should say, will give you an int. But if it's a reference, then you're going to get an L value reference. They're kind of the two main things. So then if we look at some examples here, this is kind of what I started writing up in gedit. And again, they can get pretty complicated pretty quickly. If we have an int I and then we have an int j, which is a reference to I, it's like, okay, well the decal type of I is an int because I is just a variable. I is just a standard, boring, old variable. Decal type of j though, because j is a reference, which is an L value. In this case, the decal type of j is actually an int reference, an int L value reference. And then again, it can get more complicated pretty quickly in terms of like 5 here is a PR value. And Nathaniel said this on the chat too, which is like 1 is a PR value. There's no object behind it, right? So it's like, and this is like PR values are a type of R value in the sense that we've kind of said this before, as it's like this isn't really like an addressable thing. You can't really say like, where is this object? It's just kind of floating. And yeah, there's a very tiny typo which I'll fix up later. Again, I just want to preface like this is a topic in the course that we've kind of floated about whether we should keep going into much depth on it, and we're kind of phasing it out slowly, so don't like stress about it if you don't understand it. In a lot of ways, this is mainly useful because you'll see decal type in a lot of code, which we'll kind of get to some examples of. More importantly, like rather than talking about this again too academically, I just want to kind of give you a sense of what the hell is the point of this? Like, why would I need it? I know my thing's an int. Why can't I just write int? Or why would I not just write auto? You know, like what's even the value of any of that? And here's a really, really simple example. So let's say you're writing a generic find function, and that find function takes in an iterator begin, an iterator end, and an index you're looking for, like a needle you're looking for as you loop through this linear representation of some container. Now the logic you write might be quite straightforward. You say for auto it equals begin. Yep. You also set an integer to be 0 to start. Yep, that sounds good. And then you say we're going to loop while beginning is not end, and then each time we loop, we're going to increment both the iterator and the I. So we're basically, we're basically looping through looking for a particular. Sorry, I did say something wrong before. We're looping through looking for a particular index. Earlier I said this was a needle. That's not true. Sorry about that. So if we have a list of like 10 items or something, and we're trying to go through every item to look for like the 3rd index or the 5th index, this is how we can do it. Now obviously we have STL algorithms like standard advance and standard next. I think one of them is in place and one of them is not in place. Oh my god, this chair, I love it, but it hurts my soul. Yeah, we have like standard advance, which helps us move along with standard next. So there are STL algorithms for this kind of thing. But in this case, let's say we're implementing our own for some reason. The problem with this kind of function is, what is the return type? Particularly if what you're taking in as an iterator that can be generalized across a series of types. Like what happens if you're passing in some iterator that can be the aliased or forward iterator that you could pass in a iterator to a vector, an iterator to a string. How do you know what the return type is, right? So in this case, we can't really just write in order. I mean, good, I guess, but it's like the main problem is that we could find the return type using decal type, because what do you know about iterators? Well, if you dereference begin, right, because begin is an iterator to the beginning, if you dereference it, you get the value at the beginning, and if you get the decal type of that value, you'll actually get the type. So decal type here could actually help us get some key information as to the return type. and this kind of gets into some really kind of more obscure things about dealing with this. So ideally, we'd love to use decal type here to actually specify the type. We'd be like, yep, that's the actual type I want to use. That's a bit clearer to the compiler now. We're not dealing with any kind of, you know, I don't know how to put it because this example doesn't even work. But it's like one of the more interesting things about this example is that based on the actual language rules of C++, this isn't even valid code because the decal type of the dereferencer begin. Remember that when this code's actually compiled, it does so in like a linear fashion, right? It sweeps through it. And the problem is at this point in your code here, star begin doesn't mean anything. This name is not valid yet because this name only becomes valid once it's actually parsing the function parameters. And one of the good things about the introduction of, so in C++ 11 was where they introduced trailing return types. This actually solved the problem, which is a really interesting, again, I guess, example of language design obscurities, whereby this first one here doesn't work, the second one here does work, and you'll all kind of see this familiar as, you know, the modern way of doing function return values, because at this point here, when we've used decal type begin, this is actually already been, this is now a valid name. So the compiler's like, yeah, actually at this point now I know what that is, because the way the compiler processes these is like, you know, that first value, then the function, then the next value, etc. And yeah, this is another, I think this is another reason why, I mean, I think there's a few reasons why the auto, always use auto, and the auto at the start of a function and the trailing return types are kind of starting to be encouraged. I think two big things. One that has come to my mind is like, well, firstly, there are some circumstances where the old way of specifying return types doesn't work. But I'm pretty sure in basically every instance, the new way always works. So at least there's some consistency there. Also, it kind of aligns more with, you know, most of your lines starting with auto, so that you're always looking, you know, to the right hand side or over that side for return types and stuff. But I mean, again, we don't really care what you do in that course. This is just an interesting example of decal type. Again, decal type has mainly got lip service in this course. Is like, you're going to see this around. You just need to know what it does. Are there any kind of questions before we move on to type transformations? Cool. Excellent. So, if you liked type traits yesterday, you're going to love... Oops, sorry, someone got it. Suresh says, can we do decal type auto in the loop? Yes. Oh, decal type auto. I don't know what you mean by decal type auto. I don't think you can do decal type of auto. Like, auto is not a concrete type. Or auto's an instruction to the compiler to derive the type. It's not a type. I mean, you know, don't do it. I'm sure there's some weird things about it, but yeah. I don't know what, I think like all these questions, right? I get lured into this thing where a student's like, can we do this? And it's like, why would you want to do it? It's the first question. Or like, what motivated that kind of question? Like doing a decal type of auto, what is that going to help solve? Decal type of decal type. Can you do a decal type of a decal type? I'm not sure. I mean, I don't think you can even do a decal type of a type. I mean, again, this is one of those things where you can go and try these things out really quick. I mean, the benefit of G++ and GCC and any kind of implementation of C++ is that they're really quite like easy things to play around with. So like, you know, if I were to just make a file here, I don't even know what folder I'm in. I'll go inside 6771. I'll just call it blah.cpp, right? And we just blah.cpp, and we say, you know, well, I want to make int I equals 0, and then I'll say decal type of I, j equals 0. You know, is this valid code? Yeah, that's valid code. What happens if I do decal type of int k equals 0? Does this work, right? You can just play around with these things. They didn't like that, right? So that's why, again, if you go back to the decal type docs, you can see here it's looking for some kind of, I mean, here they're referring to it as an entity, but it's essentially an expression. In language terms, expressions are, I can't remember what the difference between an expression and a statement is, but it's certainly not a type. Similarly, you wouldn't be able to do this for the same reason that, you know, decal type itself is a type. So it's basically like, I have no idea. This is not an expression to me. So it's expecting some kind of expression. Now, a little bit of an expansion on yesterday's stuff is that yesterday we did type traits, and we talked about the background around that and how it's basically you're using these structs to pass, you're using explicit specialization on these structs to give you some really cool compile time, like, how to put it, to give you some really cool compile time abilities to kind of inject like conditionality throughout your code. The reason yesterday's stuff was called type traits is because we were looking for traits of type, such as, is it a void, is it a pointer? We looked at partial specialization for is pointer, and we looked at like explicit specialization for is void. Type transformations, though, are more focused on taking a type and transforming it to a different kind of type. So some examples here are that, and we're not going to go into the mechanics of how these work. A lot of this is mainly, again, just touching very lightly on these different kinds of things that exist. So firstly, we actually have a type trait here, which is, well, I mean, the type, this is just a function we wrote, but there's a type trait called isSame. And what isSame is it's, as you'd expect, it's basically like you give it two types. So it's a templated struct or class that is templated across two type names, and all that one is that simply, like as we saw yesterday, I mean, again, I could just really quickly explain it to you if it's not concrete enough, which is like, you know, if you had something like you said struct isName, which you'd say, you know, think about how you'd implement one of these, template type name T, type name U, and all you'd have, say, under the model we did yesterday is, what was it, static, I can't remember, static const int val equals false, I think it was. I'm actually not sure how this one would be implemented, because yesterday the ones we were looking at were kind of explicit, which is really interesting. I've never actually thought about how this one's implemented because we've never bothered to go into it. The ones we went through yesterday were a little bit easier, I guess, to wrap my head around. I should be more explicit. Because we were just dealing with, where's an example? Yeah, like here we were just dealing with essentially like whether or not the type's concrete or not. So Nathaniel says that the answer to this one is partial specialization. So what, if you remember about partial specialization, is that partial specialization is where you still have the templates, you still have the type names, but you're actually in some way partially specializing it here. I'm not really sure what the syntax for this would be. I'm not sure if Nathaniel is, but the example we had of partial specialization yesterday was for is pointer. So remember how we defined our like catch-all case, our true general generic. Then we defined our partial specialization, which was still templated across the same type name, that we gave it a more explicit condition in that it had to be a pointer of that type. And that's how we dealt with partial specialization yesterday. And the point is that all these different type traits and type transformations do the exact same thing. They just go into a little bit more like variability with it, right? So this is a trait where essentially if you have T1 and T2 as the same type, this returns true, otherwise it returns false. Something that you might be wondering or asking is like, okay, sure, but yesterday when we were doing it, we didn't use a pattern like this, right? We used a pattern like, so this is what the slides have, but yesterday we did something like this, where we were like val, and you can see this here too, when these things were used. Now I can't remember which change it was. It was one of C++'s, and I don't think I put it in the notes anywhere, but I don't know if it was C++17 or one of the... There was a particular point where they made a little advancement on it, such that to access the actual value here, you could just use like a call operator or something else other than like a static member field, right? So rather than having to do whatever val, it's like this is totally valid, though I don't think it's valid for all versions of C++. And again, we could try this out really quickly just by, I mean, let's even try and just run this piece of code here. Probably, okay, so this one works fine. A.out. Yeah, so I mean, again, I could do this in VS Code. I'm just kind of doing it really quick. So you can kind of step through this. Now, standard bool alpha, what even is that line? This is something that we usually discourage, right? Again, these have a particular, actually, funnily enough, in the older version of the course, some of the first examples had these particular, I don't know what they call it, they're like terminal specifiers or something. What this first line here actually is it's kind of like changing your terminal settings. If any of you have done that thing where you put special commands in your shell scripts or whatever that give your terminal different colors and stuff like that, it's not the same as that, but it's basically like a command, because like you think standard cout and you're like, okay, I'm printing stuff, but you're not really printing stuff here. You're actually sending like a signal to standard cout that's like, oh, from now on I want you to print like ones and zeros as true and false. And you can do a similar thing to like set the number of decimal places. It's kind of like sending a setting to standard out that changes how it prints. Yeah, exactly. Yeah, Firesen says, I think decimal places has something similar. Yeah, so generally speaking, this particular thing is something we discourage the use of in the course. Though here it's mainly just done for examples, so you can see whether it's true or false. But yeah, you can see here that we call print is same. It's just a templated function with int, and we get true. We call print is same with int and int reference, or int L value reference. We get false. We get the same thing where we compare an int to an R value reference. Oops, compile. And so forth. And this is a type trait up here, right? These three things we're seeing down here, though, are what are the start of what are type transformations. And type transformations are where you essentially have a struct, just like type traits. In this case, it's called remove reference. You give it the type you're starting with, i.e. your type, and when you access a type element here, you actually get the transformed type. So in this case, it's like standard remove reference of int type. Well, int never had a reference, so this will be true, right? So the removed reference of int will be true. But then in the cases here where we have L value references and R value references, these are also true once you remove the reference, because you take an L value reference here, you remove it, you take an R value reference, you remove it, and you remove the reference part, and you just get left with the raw type. So it's like if you try and check if int is the same type as the type transformed L value reference, type transformed remove reference of the L value reference, then those two things are the same. And you can see the same thing here if you compare a const int with a constant R value reference. So these remove references are essentially, these type transformations are a way of taking in a type as a template argument and then extracting the type as a property here, right? So this is a type property essentially. Now, so I'm wondering what this is compiling with. So let me try. Okay, that still didn't mind doing that. So the compiler generally, I mean, Nathaniel's again given some more information on this. So the transition, as I understand it, is something roughly along the lines of that used to be how you would access the info. And I think Nathaniel's saying that it went to this in C++14, and I wasn't sure of the particular version, and then it's gone to this in C++17. And I'm pretty sure it's all revert backwards compatible too, so they all work, but essentially it was just like can we reduce the verbosity of this so that we're not having all this, scoped val, static, whatever. So yeah, you'll probably see a few different ways of doing this depending on the particular version that's being dealt with, because of some improvements that have been made on that front. Firesin says, would we ever need to know the implementations of type transformation functions? I mean, no, you don't really need to know the implementations of type trait functions. Most of the reason we actually talk about type traits is just as a way to understand how explicit and partial specialization work. That's kind of the aim of that stuff. So no, again, this is what I mean about it's all very academic. So it's just, this stuff again. If you fell asleep through all of this, you're not gonna like wake up tomorrow and be missing a huge amount in your day-to-day life. It's more just fun to explore the language and think about it. So there's a whole bunch of type transformations though. It's not just removing a reference, We have the ability to add an R value reference, which in a way is this is kind of like standard move to me, at least in terms of standard move. The difference is it's taking a value and converting that value to another value with a different type. In this case here, we're actually dealing with types though. So, the using keyword as a way of saying, I'd like to give this name a particular type. And again, if you think about the differences between types and values, or types and, names that denote types and names that denote values, it helps you really separate these out a bit. Otherwise, it gets really confusing really quickly. Because, you can't print A. You can't print this. This is not a value you can print. This is a type that you can use when creating a name to a value and so forth. So we have add R value reference. Same thing here, just another example here. Oh, that's where it is. I knew we put it in the slides somewhere as previously speaking. I always hate that. Because I like cutting things out of courses when I think they don't achieve a purpose. So I cut a lot out of courses as I go, because I don't just like keeping things for no reason. And then I keep thinking I cut things out, and then I'm like, oh my god, I cut that out. What was that random detail? And then it was sitting right there, and I didn't actually cut it out. But so this is like the old school way of dealing with type traits. It's the actual struct itself, and then here's this specialization. This is just a template. Maybe you're doing the catch-all case. Maybe you got the partial specialization or the explicit. This one here is obviously going to be probably some kind of these will all probably be partial. I can't imagine that the compiler has. I can't imagine the library writers have manually written explicit specializations for every single possible type, so that doesn't make sense. But the point is that from C++14 onwards, you don't need this : type thing. So you'll see like a lot of C++ code, this is okay. I'm not exactly sure on the implementation details of how this works for C++14. Obviously this one makes sense because we saw it yesterday. This is a class or a struct that has a particular static member. How this one works, I'm not too sure. But I'm sure there's some really simple solution I just haven't ever thought about, and I'd be like, oh, that makes sense. Cool. So down here's still the old school way. So you can see here in this case in C++14 and stuff, you wouldn't need this value down here. These are just older things when the method of defining those particular structs or classes was, using those static members. But again, the whole point of just mentioning type transformations is just whether it's type transformations or type traits, these are all just ways that we can, these are all ways that you can use these particular libraries to get more out of your code. For instance, if you need a type that needs a reference or doesn't need a reference, or you need to remove const or add const, etc., you can do all of that. And it's good to kind of get a sense of how they work because of all these different specializations we have with templates. Now, one of the most fun topics, I use fun in double quotes here, is binding, because, and again, I'm not sure how many of you actually watch the tute recordings or watch the tute recordings I do, and I'm not sure what the other tutors did. It was linked in the tute as like you might want to refer to this, and I haven't checked, so perhaps you know, this wasn't covered at all, perhaps it was talked about a lot. Though binding is a topic around, you know, you've got these different things, like you've got values, and you've got values, and you've got L value references, which we just call references. You've got R value references, you've got const L value references, const R value references. And when it comes to passing them into functions, what can accept them is kind of like the question. And you already have a very semi-intuitive understanding of this topic, because you all kind of know roughly that if you have a function called min that takes in, or, you know, int print that takes in an I, that you can pass in I as an int. You can pass in, well, that's I think it. You can pass in I as an int. But if you have another function called print double j, for instance, you can pass in j as an int, you can pass in j as a double, etc. And while this isn't the same thing, you already kind of have this understanding that the types that you give a function don't need to be perfect. They just need to be compatible, for lack of a better word. They need to make enough sense in their compatibility to be what you might call binded. So, like, you know, if you have a variable that you pass into this function, like I come down here and I say, you know, int k equals 0, and then I say print k, when the compiler tries to figure out which function you're trying to call, k's an int, but print takes in a double, but it's like they're compatible types, so it's kind of happy to, you know, for lack of a better word, like bind that k to that double parameter. It's like, yeah, okay, I can make this argument work. It fits my model. And the topic of binding is really all on the same track, which is that on the left here you have all the parameters that functions might take in, such as, you know, and forget the top one for a sec because we'll come back to that. You know, it might have an L value reference, basically a, you know, a non-const reference. It might have a const L value reference, which is just a const reference as you know it. And you might have an R value reference, which you probably haven't seen a ton, but you have seen it for things like move assignments and move constructors. And the idea is that if these are your parameters, if you have functions with these parameters, what arguments will bind to those things? You know, which of these arguments will work? Like, will an L value bind to a function that's expecting an L value reference? Would a const L value reference bind? Whenever I say L value or L value reference, they are the same thing, just to be clear. So when I say, you know, would an L value bind to an L value reference, you could also phrase that as like, would an L value reference bind to an L value reference? Now, obviously, this is an L value, this is a const L value, this is an R value. So an L value will bind to itself, a const L value will bind to itself, an R value will bind to itself. That's all pretty self-explanatory. The question is, what are the other cases where those things will bind together? Now, here, an L value will also bind to a const L value. That makes sense, because if you have a reference to something, you can pass it into a function that's expecting a const reference. You've probably done that before. The other way is not true, though. You can't have a const reference to something and pass it into a function that expects a reference. And again, you have an intuitive understanding of this. Like, you see this with const. If you have a non-const variable, you can pass it into a function that expects a const variable of a compatible type, but not the other way around. Because if you have a const variable and you pass it into a function that has a non-const parameter, that just wouldn't make sense according to the language rules, because it would say that that function has now permission to modify that, because in the function everything's in a bubble, and it's like, okay, the function's like, well, I have a non-const parameter, I guess I can edit it, but you can't. So that doesn't make sense. And probably the only other interesting thing is that you can pass an R value into a const L value reference parameter, because you can't modify, and you can't actually modify an R value or a PR value or whatever, just like you can't modify a literal. And again, just to really spell this out, and I mean, I'm not sure if Nathaniel, you're still around, but if you are, it'd be good if you could share a difference, because I think I got asked this the other day. It's like, what's a good example of the difference between an R value and a const R value, if that even makes any sense. But like, let's just define ourselves a function here, called print, void print, and it's just going to take in a int reference to A, right? And all it has to do is standard C out A, like this. We'll just include IOStream, and we'll just have int main, and inside int main we'll say int j equals 1, and then we'll say print j. Now, will this code compile? Yep. And when we run it, does it work? Yeah. Why? Because what is j in this case? Well, I mean, j in this sense gets treated as an L value reference, right? It's a non-const thing that we can reference. It's a non-const L value. It's a thing with an address. What happens if I make this or if I, if I maybe make this even clearer to you, it's like we have a reference to k like this, and we say pass k in, and we're like, okay, that works, that makes sense. What if we make this a reference to a const int? Will this work? No, because binding reference, see, like we're seeing all the words come together. The binding the reference of a non-const int reference here to a constant discards its qualifiers. It's basically saying, as you're like, in my attempt to bind this k to this particular parameter, it just discards the const qualification. It's saying, like, do you not care about the fact that this is const? That's not okay, so it throws an error. Now, what happens if this is now a const reference function? That works. Here's another question for you. What happens if I just try and print 6? Now remember that 6 is not a variable. 6 is an R value in this context. It's not an L value, it's an R value, because it has no memory, has no like addressable memory or anything. And when I try and do that, we get the exact same thing, right? And again, the error messages are relatively straightforward. Cannot bind non-const L value reference here of type int reference, that's what this is, to an R value of type int. So it's saying 6 is an R value of type int, and I can't bind that to an L value. It's all in this table here, right? You can't bind an L value. You can't bind an R value to an L value reference. However, what happens if this is a const L value reference? That works. R values can be binded to const L value references. And why is that the case? Well, again, it makes sense, because even though an R value is not an L value, what do you know about const L values? You can't modify them. They're like read-only. So therefore, like, as far as the compiler and the rules are concerned, it's like, well, you know what? The only problem with R values is that you can't modify them. You can't modify an int literal or a string literal. So if it's const and they can't modify it, why not? Let's just have it treated like a const L value reference. That'll make it easier. That'll make the code more robust, because your functions can work on more kinds of things. You can just define it once and it can work on a range of circumstances. And then finally, we could take in an R value reference to an int here, I believe. Yeah. So this will also work, because 6 is an R value. But what happens if you try and pass in k? Another one. What happened here? We tried to pass in a L value to an R value reference parameter, an L value argument to an R value reference parameter, and we got cannot bind R value reference of type int ampersand ampersand to L value of type const int. It won't work for J as well. Same error, but it just won't be a constant. It'll just be an int. So the rules make sense, right? Like, it's if you step through it, it's actually very well prescribed. Firesin says, how do you do a const R value? I don't know. That's what I mean. That's what I was saying before about like this is a carryover from slides time memorial that I'm trying to think. I have this memory. That's why I asked Nathaniel, because I'm just like, I don't really remember what that is. And I guess again, for more context here, I wonder if I even have them. Just a really quick, what's the time? 57. Let's finish off this topic and then I'll give you a little sneak peek in relation to that. How many we got? Yeah, okay, a couple things. So in terms of binding, this can actually be, oh yeah. So if you look at the left example here, we can actually use this to understand our code a bit more in terms of this top function here is our print function, and it is a const L value reference function. It takes in a const L value reference. Okay, so that'll take in R values, const L values, not L values though, like as in non-const L values. Now you can see here in our code, we're creating a few things. We're creating an L value here, because J is an address. We're creating a, oh, maybe this is a const R value. Is it? What is K there? Why is it an L value? Because it's a string. I thought we talked, oh, right, it's an address. Sure, got it. That makes sense. I was thinking of something else. Yeah, this is a const L value because auto will make it a const char star, and generally speaking, the compiler is happy for you to assign a string literal to a variable as long as you declare it as const, because string literals have to be const because they're not mutable. So that's all valid. And then when you say print C++, you're passing in an R value, and R value will bind to a const L value reference. Then you say print goo. Now goo here returns a string literal, so that string literal is also an R value. So therefore when you do this, you're basically taking a result of this, which is an R value, and you're trying to pass it into this, and that does work because you can bind an R value to an L value reference. We try and print J, which is an L value. That works because you can pass a non-const L value to a const L, you combine non-const things to const things. We've known about that since nearly week 1. And then K here, which is another const L value, also works. So those three things in this case work fine. And that's why you can see the const T reference binds, every argument binds to it. It's like, great, sounds good. The other relevant example though, which is a bit weird, is that the other type of parameter that everything binds to is a templated R value reference. So it's an R value reference of a templated type. I don't have a great explanation for you as to why this is, because I don't know the answer to every single y of y in the universe with C++, but essentially here the point this example is trying to demonstrate is that these things are the same in the sense that a templated R value reference, everything will bind to it as well. So in this case here, we'll be able to bind these R values and these L values and these const L values. They'll all bind totally fine. So yeah. And then we kind of get onto forwarding, which is probably the one part of the course that confuses me the most. So we'll get onto that in a sec, but before we do, does anyone have any questions about binding? I should probably mention reference collapsing, actually. I think I have that somewhere in the notes. Yeah, I'll mention reference collapsing before the break, but does anyone have any questions about that so far? Cool, found it. All right. Okay, so the last thing is just on reference collapsing. So I don't have this in the slides, but you can Google reference collapsing. Sorry, I was like, get really worried about everything, every Google I do now. I don't know, that I don't really have a true source of knowledge on it. There's some really simple rules that you can find floating around. It's not like pivotal, but it's actually, there we go, that'll do. So basically, if you're ever looking for reference collapsing information, look for something that looks vaguely like this, and you'll be like, oh, that's the correct thing. So the reason reference collapsing is really tricky is because the example we looked at, where a templated R value reference also everything binds to, right? So if you're dealing with templates, you use a template R value reference. The tricky thing is, how do you tell what the type of A is here, right? Like, and how do you tell the type of any of these things? Because like if you think about it, an R value might be like, like if you say print 5, 5 is technically an int ampersand ampersand. So if you have a function that takes in an int const ampersand, it's like, what even is the actual type of that A? And the idea behind reference collapsing is that, and I'll just copy these into gedit, is that these are the 4 rules around what happens when you essentially start stacking ampersands on top of each other. So the point here is that if you try and create an L value reference of an L value, you get an L value. If you try and create an R value reference of an L value, you get an L value. If you try and create an L value reference of an R value, you get an L value. And if you try and create an R value reference of an R value reference, you get an R value. Now, this will become more relevant with standard forward and stuff. Sorry, my eyes hurt. But these are kind of some useful rules that can help you understand what happens if, say, you go back to our type transformations where we were, did we add an R value reference? Yeah, so it's like, take something like this, where we have these lines of code here. If you take something like an int that's just an int and you add an R value reference to it, you're going to end up with an int R value reference. What happens though if you add an R value reference to int ampersand? Because this is already an L value. So like when we say R value reference, all we really mean is like do double ampersand of that, right? But you can't have just like random series of ampersands. Like it has to stop somewhere. So you can look at the reference collapsing rules, which say that, okay, well if you take an R value reference of an L value, you end up with an L value. Okay, cool. And if you take an R value reference of an R value, you end up with an R value reference. And I don't even know what an R value reference of a pointer is. I think it's just that. It's kind of an ugly thing. So yeah, these reference collapsing rules can be helpful if you come across a situation like this and you're like, wait. If I add an R value reference to an L value, what even is it anymore? And it's like the answer is an L value because the reference collapsing rules tell you. You take an L value, you add an R value reference to it, it becomes an L value. So that's like a little handy nugget of knowledge. Cool. Just before the break, I wanted to very quickly give you some fun insight into. Would everyone like some quick fun insight into the 4-minute history of Advanced C++ at UNSW? Well, it's not. We won't extend the lecture time. Well, I guess it will, but we're not going to run over. But or you just want to have your break and tell me to shut up? You tell me. I don't mind. I have no ego. Sure. Sure. So really quick, basically you have up until 2016, you have a. So what happened with this course was up until 2016, this course was, I don't remember the exact name, but I think it was called Object-Oriented Programming, right? Really simple stuff. It was, I did the course in 2013, a very long time ago when it was kind of different. Somewhere, most of this time, the course was taught by Jingling. Jingling is a pretty senior academic in the School of CSE, really crazy brain, like good crazy brain, very smart, does a lot of research in compilers and programming languages. So, this is kind of where the course came from. He stopped getting involved with it somewhere around here, and then a couple other people started to help take over it. There's a guy called Bradford Heap. In 2016, Brad ran the course, and I did a few random lectures on some topics just to fill in the gaps. I didn't have any involvement with running the course, but I just helped with a couple of the pieces of content. In 2017, they couldn't find anyone to run the course, so the course was kind of ran in the same way by, I think it was a new academic and then someone else, and that kind of happened there, and it really kind of slumped. And then in 2018, it didn't run at all. And then in 2019, uh, they wanted to run the course again, so I started running the course, as well as two other people, which was a guy at Google called Matt Stark, and then another guy who's now at Google called Christopher DeBella, who have much bigger brains than me, particularly in this field or in this language. And we kind of rewrote this course, and we kind of took a good half out of it, a half we liked, and then we made another half up, but it still followed the same general structure. And then that's kind of carried on ever since, and we've made some alterations every year. But just for like an example, so if I still have my lecture slides from 2013. I dug them up while I was talking before. And what's really interesting about the course is that it's actually like, you'll actually see how weirdly similar and different at the same time it is. So one thing, for instance, is that the course contained very similar concepts, but like the ordering of things was very different. So for instance, there was a lot of emphasis on different kind of raw types on the computers and the different sizes of those types. I think some of the earliest examples were around numeric limits. But it's funny because you'll see this and you'll be like, oh, that actually looks like a lot of this stuff looks really familiar, like type conversions. How do we convert types in C++? All right, well, we have different types of cast, but maybe there's more cast than we've talked about, or const cast. So a lot of the things that we've done, for better or for worse, it's a different kind of course. It's Jingling's. This course was a lot more focused on compilation and some of the more fundamentals of the language, whereas Chris and Matt brought a lot of their time working with C++. Clarissa says it looks like 3141. I forget what this course is. Software design and implementation. Ooh, yeah, turtle looks cute. Declarations and definitions. So here's an example, right, is that declarations and definitions came, like, remember those slides we did in week 1? It's like all of this is from this original slide deck. It's different. It's quite different, but it's like fundamentally like that's there. Topics on scopes and function scope and like local scope and namespaces. Like, so it's really interesting because in a lot of ways it's like there's a lot that has evolved and things that have been cut out too. Remember how I said earlier that we cut out a whole bunch of terminal manipulations? Things like this, for instance, where you could set the precision of decimal points and random other things. But again, a lot of very similar topics, such as argument-dependent lookup, R-value references, standard move. I'll shut up in a sec. We'll have a break in a sec. All the stuff about OOP. I did pretty bad at this course as a student. So, templates, same kind of things. It's like, it's a little bit more involved. Some of these examples, like sometimes there's entirely new chunks of the course that we've made up. Other times you'll actually see that some examples are extremely similar to some of the earlier stuff, which was, like you'll remember this from yesterday's member template stuff. So some stuff's kind of ported across, and we keep good things, we get rid of things that we think are slightly off topic. I'm just trying to find even one last one. I'm just dragging in random ones that I don't remember. Copy semantics, right? Like here's all your rule of 5 stuff. Big 5. By the way, this was 2013, so like C++ 11 was actually pretty new at the time. So a big emphasis on this course was kind of like, oh, what's all the cool things you can do with C++ 11? And how do you copy assign stuff? And really random. But I think the general gist is you can see that it was, when I talk earlier about like it being academic, it was a lot more academic in the sense that the course wasn't really focused on you building lots of things with C++. The course was focused on you understanding things about C++. Like how is it? How does the language work? How does it work with the compiler? Why certain things certain ways and stuff. But yeah, that's all. Yeah, so last question before the break. Firesin says, so next year the course will be a lot more prepared for C++ 20. Yeah, so as I said, we delved a lot into C++ 20 last year, though it caused a lot of confusion, mainly due to the lack of both teaching staff and online resources who were familiar with the topics. So there are a lot of kind of new things that we didn't feel we could support at the moment. I think what you'll see is just a slow, like you'll see like a slow creep of C++ 20 things come into this course. Like there's already a few things like, you know, the function return type notation and stuff, I think is one example. Maybe that's not to do with C++ 20, but you'll see the kind of old school custom iterators go naturally. Like if we do an assignment 2 style thing, there'll be more about or less about you know, all those different kinds of operators, and there'll be more on like the spaceship operator and stuff. Though there's definitely some quite fancy new stuff about C++ 20, like filters, which filter C++20, which I don't know what to Google to get what I want, but these were the things that very much confuse students. Like this, for instance, like this piece of code, it's like, okay, this is how you do a for loop, which takes all of the even numbers from a list, and for I don't know what this is, for I from 0 to 6, filter it and only get the even numbers, and then transform it to get the squares of all those numbers and then print them all out. So it's like, we just felt at the time that given the already uphill battle of this course, it's not the hardest course in the world, but you know, it's not an easy course, that trying to teach everything we have to teach and then to try and teach this on top is just like a bit. So, but yeah, there's plans to move towards these things as they become more widely adopted, and then there's also plans for a second course that touches on these things a bit more. Because the reality is, like, while this course is called Advanced C++, it's more really intermediate level C++ or something equivalent to that, right? Like, you wouldn't. It's hard, but it's not like, I mean, you know, you can't really have an advanced course that has no prerequisite knowledge, I guess. Yeah, anyway, that's all. So let's take a 5-10 minute break. We'll break till 7:20. We'll talk about standard forward for a little bit. It's not really going to be a massive part of your exam or any other assignment, so we won't go into too much depth with it. And then I'll have a little quick run through the assignment. We can do a little bit of a Q&A until 8 o'clock. So, yeah, sounds good.